Hello, everyone. We'll give you another minute to zoom in and we'll get started. Let's get started, everyone. Thank you for joining us today. I'm Lauren Kuby with ASU Stardust Center for Affordable Homes and the Family. And the Stardust Center seeks to connect the dots among housing, health, food access, transportation, and even shade to help craft regional integrated solutions leading to happy and healthy communities. And we recognize, though, that the opportunities to shape the future rely on the knowledge, wisdom, and practices of those that came before us. So in that spirit, we join partners across the university in acknowledging the 22 Native nations that have inhabited this land for time immemorial, including the Akmil O'odham Pima and the Pipash Maricopa Indian communities, whose care and keeping of these lands and traditions allow us to be here today. It is my honor to introduce our moderator, Philip Horton. Philip is the Clinical Associate Professor and a Senior Global Futures Scientist here at ASU, and he's currently the co-director of the new Center for Building Innovation. He received his master's in architecture with commencement honors from ASU's College of Architecture and Environmental Design. It's now called the Herberger Institute for Design and the Arts. And he's currently completing the Stanford LEAD Executive Education Program through the Graduate School of Business at Stanford University. Philip, take it away.
Thank you, Lauren. I'm delighted to welcome our speaker today, Bruce King. Bruce is the founder of the Ecological Building Network, or EBNet, and a registered engineer with 35 years of worldwide experience in structural engineering and construction. He has organized 3 international conferences on ecological building and is the founder of BuildWell Source, a user-based collection of low-carbon materials knowledge, and the BuildWell Symposia. Bruce's new co-authored book, Build Beyond Zero, New Ideas for Carbon Smart Architecture, spotlights carbon pioneers who are providing a roadmap for re-envisioning the built environment as a carbon filter, turning buildings into sites of net carbon storage. Before we begin, as a reminder to our audience, please enter your questions into the Q&A at any time. Lauren will feed them to me and we'll get to as many questions as possible. But with that, Bruce, thank you for joining us and we look forward to your talk. Bruce, you're muted.
There we go. There we go. Now can you hear me?
Yes.
Good. Welcome, everybody. I want to talk today about something that's a little bit new in the world of green building, which is the notion of not just going to zero, but beyond zero, and turning buildings into a positive force for the climate. So let's get into it. This is what we have to work with. If you scooped up all the air, breathable air around the world and put it into a ball, it would be about that big, a few hundred miles in diameter. It's basically not very much. If the Earth were the size of a basketball, it would be cardboard thin. So it's very easy to disrupt it. And that's exactly what we've done. In the 500,000 years or so that our species, Homo sapiens, has evolved away from the primate tree to who we are today, the atmospheric CO2 has been pretty steady, banging around between 200 and 300 parts per million, especially steady in the last 10, 20,000 years, during which what we know as civilization has evolved. And of course, now we're off the charts. I think the last I saw was 414 parts per million measured at Mauna Kea. We're changing the climate. And interesting thing is, even if we were to stop burning fossil fuels on a dime tomorrow, we would still have a problem because they'd still be going up. The methane released from the Arctic, the change in albedo in the oceans, a number of things would have a carbon emission engine still running. So besides getting to zero with our emissions, we need also to bring it back, get the carbon back out of the sky and return it safely and durably to Earth. How would you do that? If you can get all the carbon out of the sky, where would you put it? Well, one of the places by default is the ocean. They're absorbing about 40% of what we put up there, which isn't nearly enough to halt climate disruption. And it's disastrous for the oceans because it changes the acidity of the water and destroys corals. And I'll bet you know about all this stuff already, or at least something. We can also inject it below ground, pump it underground. And in fact, oil companies are doing that at some scale right now, being paid by the US taxpayer to do so as a climate benefit thing. And usually what they're doing is recharging their own oil wells and getting some more oil and gas out of the proposition. Nonetheless, you can get a lot of carbon underground. It remains to be seen whether that'll ever be economical. There's a whole bunch of people working on soil, that is agriculture and regenerative, or not just organic, but regenerative agriculture that recarbonizes the soil that we've stripped of carbon over the last century. Another huge repository. What I know about is buildings, and it turns out that they stand poised to be a huge repository. When we get the carbon out of the sky, we can turn it into buildings. And here's why. There's a lot of buildings. We make a lot of stuff. The building environment, the construction industry uses far, far more physical stuff than any other industry. And we are at present building the equivalent of another New York City every 35 days, which might seem kind of incredible to you sitting in Arizona or anywhere in North America, because it's not happening here. If you happen to have traveled to these 3 cities, among others, as I have in the last few years, you probably had your jaw dropping to the floor with the pace of activity, the pace of construction, everything about it. Cities like Cairo, Sao Paulo, Beijing radically transformed just in the last few decades. And that's where all this construction is happening, and it's mostly concrete and brick. Some basics. Buildings account for about 40% of greenhouse gas emissions by many people's estimation. Kind of fuzzy, it depends on how you define things, but that's the general number. And they come in 2 forms or 2 phases. First, there's so-called embodied emissions, the greenhouse gases that go up in the air just in the process of making the materials you're going to build with. They happen right at the start, and then everybody moves in and they start operating the building. You turn on the lights, you turn on the air conditioner, and the operating emissions. And over the life of most buildings, over 40, 60, 100 years, those operating emissions will dwarf the embodied emissions. And so that's what the green building community has been focused on for the past 30 years that I've been involved, getting those operating emissions down to 0. Thus you hear get to zero, net zero buildings, passive house buildings. That's all great. We have a pretty good sense of how to make net zero buildings now. We don't, but we know how to anyway, and it's a start. But we're not worried about the next 60 or 80 or 100 years so much, given that we're in a time of climate emergency. We got to move fast and hard now. We're worried about the next 10 or 20 years. And in that context, things change quite a lot, and the proportions completely change. Not only are those embodied emissions from the materials much larger by proportion, but they have a time value. It's how long they're in the air cooking away, as much as how big they are. So the embodied emissions are maybe 12% of global emissions, but in fact, they're more like 20 because you have to also include all the infrastructure that we surround ourselves with. You're sitting in a building made of a whole bunch of stuff, but you probably came here on a highway, and there's sidewalks, there's pipes, there's power lines, there's power stations, all the stuff that supports the buildings we live in, supports our lifestyles. The infrastructure accounts for about 20% of global emissions, 1 out of every 5 tons of emissions. That has a time value because it happens now. It's not attenuated over years of operating a building or operating anything. It's in the air already by the time you finish the project. So if you remember anything from this talk, it's this. My colleagues at Architecture 2030 ran a bunch of numbers with a bunch of different building types in a bunch of different climates and came up with this number. If you build something today, in addition to your house, a new high-rise in Manhattan, also any kind of building, generally, most of your climate impact is from the materials you chose to build with, the embodied carbon of construction, not from the operating the building. That's where the action is here in time of climate emergency. That's where we need to pull our attention. So how do we do that? Well, there's 2 basic kinds of building materials, either minerals or plants. Let's talk about them both. Minerals are pretty simple. It's metals and concrete. Steel predominantly, but copper, aluminum, lots of other metals. In fact, we use just about every metal we know of in one way or another in buildings, mostly with electronics, but steel in great quantity. 6% of global emissions are for steel. About half of that is for buildings. And the steel industry, in a sense, is very progressive. They're already recycling at a very high rate. But nonetheless, they need a lot of energy. They need a lot of intense energy to melt the metal and recycle it. That's all there is to it. There's no substitute. Nobody's perceived a substitute. So it looks like the only way to improve in the metals industry, especially steel, is with hydrogen. You've heard about a hydrogen economy. It's coming. A lot more progress in Europe than there is here. A lot of resistance because the industry is going to have to spend some money, but nonetheless, a hydrogen economy will be the key to a climate-friendly metals industry. Concrete then is a whole nother story. Concrete is a huge industry. But to start with, understand that concrete is just artificial rock. You glue a bunch of little rocks together, sand and gravel and glue, and you get all the things we make. But everything we make is out of earth. It was all pulled out of the surface of the earth in one way or another and transformed biologically or industrially to become the World Trade Center or a teepee or the Pantheon or any other building you've ever been in. It's all earthen construction. The key to climate friendly is just to simplify and shorten the supply chain. Concrete is by far the most predominant building material on earth. It's what all that new construction, that new New York City every 35 days is mostly concrete. Rock, sand, and glue. Take a bunch of little rocks and turn them into a bigger rock. That's concrete. Well, how do we do that? Well, one glue is Portland cement. It was invented 200 years ago. It was a technological improvement on the lime plasters that had been around for millennia. And it's a really cool building material. It's bomb-proof. It works really well. You can screw it up and it still works, except that you have to make it by baking limestone at very high temperature. And so it has a huge climate impact. Clay is another glue. It's a traditional glue that we make concrete with. Thus, earthen architecture is basically clay concrete. But Portland cement has a problem. You bake all that limestone like that, and you get an industry that accounts for 7% of global emissions. The concrete industry is attributed 8%, but it's a big chunk. If concrete were a nation, it would be the third largest emitter on Earth. These are all concrete buildings that didn't use any Portland cement, and they're doing just fine after 1,000, 2,000 years, some of them. These are buildings that use Portland cement and aren't doing so well, either bad design or bad construction. Point being here that we're returning to looking at earthen construction, clay-based concrete, in many ways now as a substitute for Portland cement concrete, which predominates all over the world. In fact, it just got a big prize. The highest award in architecture, the Pritzker Prize, was just awarded a few weeks ago to Francis Carré, in part for all of his wonderful work with natural materials, natural wood, clay, sand, and straw. So Earth is having a revival. But Portland cement concrete is really the big game on Earth. It's a gigantic industry, 10 billion tons a year. Well, how big is that? Who knows, right? You hear big numbers all the time, and you don't know what to do with it. 10 billion tons, how big is that? Well, how big is 1 ton? 29 inches, it's the height of a desk. A cube of concrete that weighs a ton is desk height exactly. So how big is 10 billion tons? If you guessed a mile, you'd be right. It's a mile cube, 5 times the height of the Eiffel Tower. And that's how much we human beings are making and placing somewhere on Earth every year, 10 billion tons of concrete. It's pound for pound, very low carbon building material, but 10 billion tons of anything is going to start to add up. So how do we improve? Well, the industry is working really hard, really fast right now to improve, changing cements, changing all sorts of things. A lot of tech money, a lot of venture capital money, a lot of policy work going into changing concrete because everybody can see this is something we need to do and fast. Mostly it amounts to making it with carbon, turning it into using emissions and turning them into our concrete. Rather than baking limestone, what if we took the emissions and turned them into the gravel that constitutes the bulk of the concrete in the first place? And there are a number of companies working on doing that. But to do that, you have to have the carbon. And thus you see pictures like this of these giant metal contraptions that filter carbon dioxide out of the air and turn it into gaseous or liquid carbon dioxide. And if you're like me, you probably thought, oh, what silly people, don't they understand that trees are doing that all the time for free on solar energy? And so is the straw on the fields where we grow our food, which is true. But they can't give us the carbon dioxide as a feedstock to turn into all sorts of different building materials by which we can actually store atmospheric carbon that's up there cooking right now and turn it into stable buildings, hard core stuff. Then there's straw. Concrete is a mile cube, straw is nearly 2 miles. All the straw we harvest, growing our oats, barley, rice, rye, all the grains that we grow and eat, the bulk of our food stuff. The waste straw that's left over after you take the seed head and eat it amounts to a cube nearly 2 miles in size every year, half of which is carbon. What if we could turn that into buildings? Well, let's look at minerals and plants. Straw bale construction. You've probably heard of it. It's invented in the United States 120 years ago on the plains of Nebraska by the early settlers there. Fell out of use when the railroad came through and brought other materials, but enjoyed a bit of a revival starting there in Arizona 30 years ago. And now it's all over the world. People are building straw bale buildings everywhere. And it's fun. It's a very quirky community building, fun kind of thing. And it also makes a very, very effective insulator. Straw bale walls are really, really comfortable walls to have for your home or for any other building. But you're not going to build another Manhattan every 35 days out of bales of straw. It's just too funky and irregular and all of that. Hit the wrong button. What you can do is turn the straw into building products. And there's a vast family of products already appearing all over the world from many countries. Canadians, the Europeans, the Kiwis, everybody making straw panels, straw blocks, straw insulation systems. It's coming on strong into our mainstream construction economy. The French perhaps are ahead of anybody, building some lovely and elaborate buildings that by looking at them, you wouldn't know they were made of straw. And likewise are the English and the Australians. Another way to build with plants is wood. Of course, it's been around forever, and we've done a million things with wood for centuries. But since World War II, when we figured out how to cut and fit and glue wood together, starting with plywood, and then glue lam beams, and then all sorts of wood products that you see on the shelf at Home Depot now. That has evolved to mass timber, where the possibility exists to do the large buildings that define midtown of any city in the world. The hitherto could only be done with concrete or steel. You could only go so high before natural materials couldn't do it anymore. And if you want to go high, which I have some problems with, but that's another conversation. Now you can do it with wood, all wood buildings, mass timber. You can do really elaborate stuff like in this picture, and very just ordinary rectangular stuff that works out really well and costs out really well. So mass timber is coming on strong in the industry and gets a lot of claims to be the climate-friendly alternative to steel and concrete, which it often is, and it's often not. Depends on where you are and where you're getting your wood. And you can get wood from certified sustainable sources that protects the forest and leaves something intact. But a lot of it is not that way. And so it's a mixed bag with mass timber. Can be a good thing, but not always. And there's hemp. It's a weed. It grows everywhere, like a weed. A fabulous plant. You take the leaves and you can make clothing and all sorts of stuff with the leaves. You take the seeds and you can make oils and medicines and food out of them. They're very rich in protein. When you take all that stuff away and you do everything else you can with it, all you're left with is the herd, the core of the plant. Take that and chop it up, and it turns out to be a great building material, a very durable fiber. That's why we have hemp rope for centuries now. Hemp rope because it was stronger than any other fiber. Now we're combining that with lime plasters. Chop up the herds like that, mix it with lime, and pack it into a wall or make blocks out of it, or make entire buildings. And there's plenty of buildings now in the UK and France, and starting to be in the US, made with hemp and hempcrete, as it's called. There's a whole hempcrete association in America now, hundreds of members last I checked. Then there's another bespoke plant that we can grow specifically as a utilitarian plant, especially for building. Bamboo also has been around for a long, long time. It's an indigenous architectural system in a lot of the world, especially the South Pacific. And now it's enjoying a revival. Some really elaborate things from South American architects, Simón Vélez and Oscar Hidalgo. Really fabulous, fabulous things. Not exactly affordable housing, but sure fun to look at and be in. But now we're also figuring out we can take this very lumpy and irregular grass that is bamboo and grows so quickly and smush it together like we learned to do with wood and glue it back into rectangular systems where you can have an affordable, pardon me, and very energy efficient structure made entirely out of bamboo. So watch for a lot more happening in that realm. Here's sort of the wild card that's just starting to show up on anybody's radar. In practically every industry, right? We're making artificial meat with algae and bacteria now, and we're also making building products, copying what we learned from nature. It's biomimicry at work. This is a termite mound from Africa. There's similar ones in Australia, other places. And the termites just take earth, chew it up, and the bacteria in their saliva binds it together. It's a cement. And they build these huge structures, which, by the way, are not their homes. This is an air conditioning system. It uses the natural breezes to maintain a constant humidity and temperature inside the hive below ground, below this thing, for the termites. We still have a lot to learn about how to build, in other words. And we've taken the idea, and there's a company now in North Carolina, Biomason, that's growing concrete with bacteria. They're going great guns. They're having great success in expanding. I think last I heard they had a contract with the Department of Defense to provide bricks. This is as strong as any concrete you've ever seen and made at room temperature and pressure with bacteria. So we're just starting to find out what we can do with microbes, basically. The third general category being fungi. Ecovative up in New York has learned how to make artificial insulation and packing materials by taking whatever cellulose you have handy, some sawdust, some wood, mixing it with their magic sauce, and it grows into place, fits around anything you want. All these wood systems with all these different plant materials, most of which are agricultural byproducts from what we're growing anyway. Softwood forests, you can get 2 to 4 tons of carbon per hectare per year. Straw, maybe a little more. Hemp, quite a bit more, depending on how often you harvest. But algae, this is why it has the huge promise, is that with hydroponic structures, we can be sucking carbon out of the air at a huge rate and turning it into food and buildings. That's why I always say the little ones to the rescue. They're going to save us in more ways than we can imagine right now. I'm sure of it, because we're sure not saving ourselves right now. There's always a few wild cards. You got to stick your head up and look around. You know, what's the context in which we're working? What's going on? The big one, of course, is we're living with hockey sticks. Hockey stick of human population growth, hockey stick of computing power growing, hockey stick of atmospheric carbon, all sorts of them. And you and I are living on the crux point of that. And here's the thing, you're living on that crux point. You think it's going to keep going about like that because you predict the future based on the past, but it's not going to go like that. It's going to go like that. And so we don't know how a lot of these things are going to go, including artificial intelligence and robotics. They're going to have a huge impact on the construction industry. They already are. You read about 3D printers that can squeeze out a whole entire building, or smaller ones that just make components out of all sorts of interesting materials. The one on the lower left is salt blocks. 3D printed salt blocks. And so you can imagine a construction world that's full of robots of every size and scale, from the huge ones that can do a whole building to nano robots running around cleaning and sieving and sorting things. The pedestrian stuff that's part of any construction project, and these machines can do it for us much faster, much better. Is it a good thing? It is a bad thing. It puts him out of work. It's probably going to be a mix of everything in the world to come, but it's going to be interesting to see how that pans out. But what's very clear is that we're going to need to transform from a hydrocarbon economy, the hydrocarbons we dug out of the ground from ancient plant life, to hydrogen and carbon separately provided and made available to us. Hydrogen is a way of storing solar energy or wind energy that you harvested at some point and delivering it intensely to somebody who needs it, like a steel plant. And carbon available as a feedstock to make not just building materials, but clothing, food, plastics, everything. What can you do? You hear about your carbon footprint. Yeah, reduce it, sure. Eat less meat. Be conscious of what you buy and buy less. Drive less, ride your bicycle, all these things that you hear for sure. But it's just as important, maybe more important, to think about your green handprint. What are you doing for the climate? What are you doing to make a positive impact? Organize your neighborhood, join some group. I don't know what it would be for you. For me, it's been an interesting adventure. But if that's what you're looking to do, believe me, the opportunities are going to show up for you at any scale, at any place you may be. And with that, I leave you. Oh, and if you want to read more, our book just came out. Chris Magwood and I finished this book during the pandemic, Build Beyond Zero, and its official launch date is today. So if you want to read more about all of this stuff and more, get the book, and I hope you enjoy it. And with that, I think I'm done. And
Bruce, thank you so much. You were given a 25-minute window, so you did a great job of cutting through mostly, I think, chapters 4, 5, 6, and 7 of a 14-page book that I had the great fortune of getting an advanced copy of and have had a chance to read, and it's fantastic. And I think there's so much more depth for folks to be able to get into within the book. I do have a question for you, but before jumping into it, we ask that the audience use the Q&A feature to submit questions, and we'll cover as many as we have time for. But my question for you, so what's kind of fascinating for me in reading the book is that there is at once this like incredible optimism about the opportunities for positive change through material science, through procurement, manufacturing. And then there's a bit of pessimism, understandably so, about policy and economics and sort of the human side of accepting, embracing, and running at change. And you talk about a number of protagonists within the conversation, folks like the Architecture 2030 group, I think it's SEI, the structural engineering group, even a group of students at Dalhousie University. The struggle there is a little bit that folks are working within their spheres, within their silos. Where is your optimism for people working collaboratively across the value chain of buildings, everything from policy and finance through life cycle management of buildings, and what can we look forward to on that side of things?
Well, first, a little correction for those of you who are wondering, it's not a 14-page book. It's a 14-chapter book, but
sorry, 14-chapter book, yes.
You get more for your money than 14 pages. But it's ever more evident to me that though there are lots of interesting technological problems to work out, and that's where I work. I'm an engineer, I'm a materials geek, and I work with a lot of really delightful people all over the world. But that's not going to get us anywhere. We have all the answers we need. I mean, this is how I finished the book. Chris and I finished the book. We already have the technology we need. I'm sure more technology is going to come. It should be interesting and it'd be fun. But if we didn't get any more at all from this point forward, we'd probably be okay. What we don't have is the political will. It's going to be some sort of, I hate to say it because it's already a trashed term, but an awakening. You're going to have to choose love and compassion. And you're going to have to choose love and compassion in the face of, God, what did I hear something recently about? This may seem a little airy-fairy answer to your question, Philip, but it's the only answer I've got, is we all have to choose compassion. Somebody was talking to a man a very old Black man who had known slavery. Somebody recorded a conversation with him long ago, and when some situation come up and an awful situation, but he said, when everything in you wants to choose hate is when you have to choose love. We're all going to have to rise up above whatever circumstances may be bothering you. And, as I'm a white heterosexual male in America, I don't have a whole lot to complain about, but life is hard for everybody. And we all get a little freaked out by everything going on, and we're going to have to rise above it. That's the hope that I have. Or to borrow from the science fiction writer, Kim Stanley Robinson, I quote him at the end at our final chapter, and he says, and this is quoted from a book that's from the 100 years in the future. And the guy says, he's a trader in New York 100 years now. He says, if you want a short civilization, that's fine. That's a smart bet. Every indication is that we're going down. He says, but trouble is there's nobody there to pay you if you win. But if you go long on civilization, it means not only do you win, but everybody's still here and you get to have a good time. So that's the smart bet, is go long. Be optimistic because nothing else makes any sense. And be compassionate with courage and conviction and alacrity. And that's my best answer to your question. All the technical stuff and policy, I'm involved in policy stuff. It's dreary, it's awful, and it has to be done. But something's going to shift, and I don't know where it's going to come from. I really don't.
No, it's fantastic. So some of the questions from the chat. First question is, why do we use so much Portland cement? Is it cheaper? Is it more abundant? What is the impetus there?
Well, it's relatively cheap for us here in poor parts of the world. I've worked in Haiti and a lot of places. The other end of the world where people are poor, it's fairly expensive. It's a week's wages to buy a bag of cement, but nonetheless, they use it a lot. And we wrote a low carbon concrete building code here in my county, Marin County. My building official and I teamed up, and something came together because I knew after it's been 44 years of practicing structural engineering now, that every concrete on every job I'd had ever done, and every one of them had concrete, had more cement in it than it needed. I didn't think about it then. The guys who trained me said, oh, just make sure they got at least 5 bags of cement in there, or just make sure there's at least this and at least that. Because you don't want to get a callback. You don't want something to go wrong. You want the concrete to be really, really strong. And so just routinely, right around you there in Tempe, if somebody is calling for a certain concrete, like to pour a sidewalk, and the engineer might determine that you only need like a strength of 2,000 PSI, but very likely the strength of the concrete that you're going to end up getting is going to be 5,000 or 6,000 PSI, meaning many times stronger than it needs to be because it has more cement than it needs to have. And there's reasons why people do that. It's not quite so simple, but I knew that in the industry, we were routinely, we were just accustomed to using lots of it because nobody cared. It didn't cost that much, and it insured against a callback. We can't do that anymore. We have to pay attention in my industry, and the industry is changing. For as big a behemoth as it is, it's changing pretty fast.
Well, in that particular chapter is fantastic because you essentially write to structural engineers, to suppliers. Like you're very specific about recognizing the different stakeholders in that portion. So thank you for that. The next question here, what is the single most important thing cities can do to encourage or incentivize building beyond zero?
Change your procurement policies. Most cities are one of the major buyers of construction services. And in fact, we're seeing a lot happening that at every level. You've heard of the Buy Clean Act in California, which I'm working on amending right now. The General Services Administration, the federal government, just put out procurement guidelines. So when they, who build a lot of stuff and maintain a lot of buildings, are buying concrete or steel or carpet or gypsum board, it has to meet certain standards, fall below certain thresholds of global warming potential. It takes a little bit of finesse and work to write the details of such laws, but in concept, it's pretty simple. If you're gonna bid for our jobs, you're gonna have to come in below a certain threshold and show that you're paying attention to the climate. So for cities, and I'm working a lot with New Buildings Institute now, who do a lot of code and standard work. And you could refer to them because they do a lot of work with a lot of cities. We did something here in Marin County, but it's a little bit unique. But anyway, procurement guidelines, and then after that, amend the building code. But we're going to have a model national building code in a few years that any city can adopt. But in the meantime, procurement guidelines for sure.
Well, and in the book as well, you talk about how the kind of model codes, the national codes, still need to take into account a lot of local considerations. So having that local level, let's say, intelligence is critical, and you've advocated for it here as well. The next question, it says, preparations for preventing wildfire in our county in California is well underway. How do the new materials measure up against today's building materials in hardening homes?
It's hard to make a blanket comment, but I could only address the one that comes up quite often, which has to do with straw in construction and straw bale buildings. And in fact, they do a lot better than stick-built buildings in fires. That's demonstrated both by tests. I organized some tests at a fire facility in San Antonio 12 years ago, but also by experience in the wine country fires that we've had in the last few years. More than a few straw bale structures came through just fine, while wood frame buildings near them didn't. Wood framed buildings are great for earthquakes. They're without equal because they just give and they absorb, and they're just perfect for earthquakes because they can absorb the energy without falling apart. And they're absolutely terrible for fire country. And I'm sure that in a generation or so, we'll be looking back and saying, what were we thinking? We build our houses out of kindling. And then on top of that, we run pipes in there with pressurized flammable gas into various rooms just to make sure things will really go down hard. Earthen construction looks like a good solution. It's a very good solution in Arizona. It's trickier in earthquake country because clay-based concrete isn't as strong, so it's hard to make it work in the earthquake, but we do know how to do that too. That's going to be a longer slog, but that's the short answer. Generally, you can't make a comment. I mean, you can build with natural materials or with climate-friendly materials and be very fire safe. That's not an issue at all.
You raise a really great point that one of the barriers to getting new materials out to, let's say, broad commercial availability is that it has to go through a lot of different testing before you can get there because of life safety, which is obviously paramount. So we have a fourth question here from Jack Gilchrist, who's a landscape architect who's also taught our professional practice course to landscape architects for a number of years. It says, as a landscape architect, our profession is promoting expanding our urban forests as a good way to capture carbon. Any thoughts about this?
I agree. And in fact, in the book, there's a 8 or 10 page contribution by Pamela Conrad, a local landscape architect who's really been a pioneer in your industry for, how do we practice landscape architecture through the lens of climate emergency? What can we do? Planting more urban trees for sure, conscious of how you use concrete, making reuse of things that are already present on the site and so on. Pamela's really fabulous. And so there's some stuff in the book about that, but for sure, having a lot more greenery in cities. Every imagination or depiction of the city of the future, the cool city of the future, not the dystopian one, they always involve lots and lots of greenery up and down the facades of buildings, the roofs of buildings. No doubt about it. That's the way to go. We just have so much concrete now, and nobody really likes concrete that much, but it's everywhere.
Well, and you raise a couple of things. One, in the book, you talk about the rate at which trees will suck or draw down carbon from the atmosphere, but you also then compare that against hemp, against other plant materials as well as algae, and it seems quite clear that we need a multitude of ways, both kind of living technologies and human technologies combined for both multiple purposes and to draw as much of it down as we can as quickly as possible. You also raise up a really great point that the book is filled with a series of what are referred to as boxes throughout each chapter, in which other voices, Kate Simonson writes the introduction, and then there are a number of other fantastic voices that are distributed throughout the book, talking about related issues or going deeper into some of the topics, and in some cases connecting to other really critical topics. So then we have another question here. It says, what are some pressure points to get federal policies to implement what we know, construction material, sorry, let me read this question. What are some pressure points to get federal policies to implement what we know? That's the question. Construction material, what you just spoke about. I think it's really just generally a question of how do we make, how do we get policy to be more progressive in reacting to the thing that we have so much information about?
Yeah. Well, there's basically good news here. There's been a lot of policy work in various departments of the federal government. I was part of a ad hoc Green Building Advisory Committee to the GSA that led up to their announcing their procurement provisions. And I think that they're going to take that further. And there's also ASHRAE, what used to be an acronym for something, but now it's just known as the organization that writes the Green Building Code, or Standard 189, that is the basis for the Green Building Code. And I'm part of a lot of work there to address all the issues I talked about and many others, and improve and green up our construction industry. And you'll be shocked to hear that entrenched industry is not exactly going along for the ride freely and sweetly. They're very clever about how they resist it, but they do resist it and slow it down as best they can.
Well, I think there's an interesting bit there's a whole chapter on policy, and I think you referred to it as 21st century cat herding. I want to make sure I get that right, but the interesting thing within it is you talk about the need for there to be policy change up and down the scales. So everything from local, looking at who's doing the commissioning and permitting at the local level, all the way up to those national guidelines. And in many instances, it's not just about, in some cases, policies changing that are very specifically measured or enforcing things like what you argue should be whole building regulation, thinking about the full life cycle of buildings and projecting what the carbon impact of that will be over its whole life cycle, and trying to hit certain targets. But there are some things that are also sort of baked into local policies that in many instances inadvertently are going to give favoritism to some technologies over others. And one that comes to mind just personally is that when you have zoning ordinances that say that you have a max building height that you can build up to, in many instances, then having the thinnest possible floor plates and having the most compact possible services, if they live between floors, might give you a chance of getting an additional developable floor under that max height, which then is going to disadvantage things like mass timber or other material systems that might require something thicker than what say a post-tension concrete slab is going to require. So in some ways, what's great about that particular chapter is that you're talking both about what are the changes that need to happen to incentivize those kinds of changes, but also what kinds of penalties need to exist within the code system. And maybe you could talk just a little bit more about policy from that lens, the kind of sticks and carrots, if you will.
Yeah, sticks and carrots. It's relatively easy to write rules that say thou shalt not. It's really tricky actually to write policy at a local or a national level that says you get these goodies if you do the right thing, store carbon or cease emitting or get to zero or something. That's a lot harder to do. I completely agree. I think maybe the most of the zoning laws extant in America today are may be one of the biggest drivers of emissions that are in the built environment there are, period. They're horrendous. I live in a suburb of San Francisco, lands taken from the Aguasta tribe of the Miwok Indians. And when my wife and I bought this house 15, 16 years ago, we sat in a realtor's office signing dozens and dozens of documents, just stacks them, and you just start flipping through, and your eyes glaze over. But I'm sure at some point, I've never gone back and checked, but at some point I flipped through something, I looked at it, really, it was something excluding Black people. This is for white people, it's not for, they are excluded. And I think it's still on the books here. And nobody would enforce it. It's not enforced. It's Black people here. But that sort of stuff is baked in all over America, especially in the post-war years after World War II, when these zoning laws were written. But there's some insidious parts of it too, where people are driving a particular racist agenda or a whatever. Politics is ugly stuff. I don't have a simple answer to your question. I'm a materials geek, and my life is relatively easy. How do you make lower carbon concrete and stuff like that is comparatively easy stuff. To writing the rules that start to move the ship of state around, and so we're not driving so much, and we have trees in our cities, and everybody has access to decent, not just homes, but healthcare and transportation and all of that. It's a bit of a mess, but things are shifting. And as I say, there's stuff that happens in governance at every level that we hear about and are outraged about. And there's also stuff that happens that's really cool and you never hear about because it's just not newsworthy. The papers, nobody prints it because nobody cares. It's just not that interesting. The Environmental Protection Act, a lot of things that happened under President Nixon were really cool. And it didn't get that much fanfare because, Clean Water Act, the Clean Air Act. And there's stuff like that still happening in the government. The Green Building Advisory Committee that I was on for the GSA, that started way back in the Trump years. I couldn't understand, how is this happening? But it was.
So a couple more questions here. One says that School of Sustainability graduates from ASU have worked to get sustainable building materials approved in what seems to be an expensive and complicated process. Can you describe some of the barriers to the introduction of new materials?
Oh God, it's a bitch. Because I've worked on that. I've gone through the testing programs, the fire tests, the structural tests. It's very, very hard to get a new material approved in our present system. I have long conversations with my own building official about this. We have lunches together, and that's what led to our doing the low carbon concrete code. But it's as much as fear of liability on various parties' parts as anything. But natural building materials like straw bales or clay concrete, earthen building, or bamboo or hemp, they face a tough slog to get real legitimacy and show up on the shelf at Home Depot, literally and metaphorically. And I don't know a way around that. We've become, it's a very tricky thing. As I start that chapter on governance with brilliant insight from E.O. Wilson, the biologist, who said our basic problem is that we have Paleolithic emotions, medieval institutions, and godlike technology. What could possibly go wrong? What could possibly go right? So we're in for a major shift in the way we govern, at least the built environment, if not ourselves entirely. I certainly hope democracy will survive, as lumpy as imperfect as it is, but how we manage the built environment is already way, 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 way more cumbersome than it needs to be, or than is really serving anybody. Which is all sort of dancing around the question. Basically, if you want to introduce a new material, have legitimacy and show up in the code and be on the shelf, you got a lot of work to do, a lot of time and a lot of money.
Agreed. So we have another question here that I think you reference in the book through a couple of different lenses, but I'll read it as it's written. It says, can you discuss your thoughts on agricultural land integration with building and city design?
Yeah, I can. I hear people talk about these things all the time. Like, for instance, if you're going to use straw bales to build with, are you going to buy them from an industrial agriculture operation or from an organic farmer who's trying to store carbon in the soil? And I know people who are earnestly trying to draw the distinction and do that. It gets really tricky really fast, but more to the point, who's in charge of land use problems? We have a free market economy. You know, America is very proud of like trying not to tell people what they can and cannot do with their land. So it's an abstract argument to say, well, in the ideal, we've had the city should be this and the farm should be out here. And we can draw lots of pretty pictures when we're in college. But the reality world is so much more messy. Nonetheless, we can write policy to try to guide things in a certain direction. So the question is still worthy. And I'm not sure I know the answer. Certainly the way we grow food in parallel to the way we're building buildings right now is just not working, or it's not going to work in the long term. It is literally not sustainable. The farmers are drying out the soil. I got a tour of a rice straw field 15 years ago when I was first writing about straw bale construction, and the farmer just pointed out this vast flat fields around him in the Central Valley of California. He said, the soil is completely sterile. It is just a canvas upon which I dump fertilizer and nutrients and then grow rice and then dump more on them the next year, because we stripped the soil a long time ago of any life. And he knew it just couldn't last. He knew it couldn't, but he didn't know what he could do about it as a rice farmer. So a lot of us have gotten stuck with the system we've got, and it's, you know, we got each of us have to find a way. I mean, each of us occupies some special spot in the ecosystem, and you might be the one, whoever you are listening, who can find a little crack and so work into that crack and say, maybe we could lever something here. We could make something change here. Like in Marin, we wrote this low carbon concrete building code because the building official and I were thinking about this, and we agreed about it, and we had a progressive political environment around us, and we thought it's not going to change the climate. We don't pour any concrete here. We're just a little suburban community, but maybe we can make a splash. Maybe we can have effect. And in fact, it did have that, and people call us and want to read about it and learn about it, and it's modeled now. So I'm pleased. I'm happy about that. So each of you, each one of us, look for what you might do. There's always a crack in the system. There's always a little crack in the rock. That's how people climb El Capitan, because there's cracks in the rock.
Sometimes with no ropes, which makes my hands just watching it. But
not me, pal.
So, there's one last question we'll try to squeeze in, but beforehand, there was a question about where the book can be found, and Lauren has pasted in the chat where it can be found at a local bookshop called Changing Hands. The book was published by Island Press. But the question here, it says, you mentioned building operating emissions are the greatest source of building related global carbon. Does your book discuss how to reduce building operating carbon emissions?
No, we hardly do more than mention it, simply because it's gotten so much attention in so many books and so many journals and so many conferences. Like I said at the start, it's been the focus of the green building movement for 30 years. And so in these 30 years, we've gotten really good at making very energy efficient buildings. And in fact, our average energy use per square foot in America, and I think in the world, has been improving steadily for many years now. Because eventually we started writing codes, we started requiring insulation and air tightness standards and efficiency of heat pumps and lighting systems. All of that stuff has improved because somebody started banging around for efficiency and say, let's improve all this stuff. And so it has shown up. It has made a big difference. But that's completely covered elsewhere. We didn't need to redo all that stuff. We said, hey, there's something over here we need to pay attention to. And not only is it, you know, I first wrote about this. I wrote a book called The New Carbon Architecture 4 years ago. And what Chris and I have done builds on that and expands on that with Build Beyond Zero. But it's a new notion saying, look, we've been ignoring the embodied energy, the embodied emissions of buildings because it didn't seem to amount to anywhere near as much. But it turns out it amounts to a lot for the time value and for other reasons. So we focused on that, and that's what we talked about. Let other people talk about the best insulation systems and all of the things related to operating energy. So
No, and that's a really great point, and that's why there's a great deal of emphasis on LCA, life cycle assessment, and even a critique that it doesn't really adequately account for the time value. So then you introduce this WBLCA, which is fantastic, as well as notions about not just thinking about renewable energy, but renewable building materials. And there is, towards the beginning of the book, a brief history of green building, which, while it doesn't get into reducing carbon emissions or getting to zero, it does quickly talk about these things are all important, but zero is not enough. We have one last question. It says, driving the built environment to net zero carbon by 2050 is insanely challenging, considering we renovate less than 1% of our North American portfolio. Does the book cover these steps?
Yeah, and the book not only covers those steps, but it presents a challenge to the whole construction community with a chart and with a background for how I came up with the numbers that we not only can get to zero, but we have to do better than that. We have to build beyond zero, and that we can be storing 15 gigatons a year by 2050 if we set our minds to it. I don't think it'd even be much of a technological challenge if we set our minds to it. So who the hell knows what's going to happen in the next 25 years? There's so many wild cards at play and hockey sticks at play, but that possibility is there. And in fact, is what we need to shoot at. Shooting for net zero is a losing proposition. If we shoot for net zero by 2050, we lose, and our grandchildren are screwed.
Agreed.
Let's do better than that. Let's do better than that. We can.
Well, Bruce, I want to echo what has been mentioned in the chat many times, which is that this has been a really great presentation. I want to thank everybody who joined us for their great questions. Thank you again, Bruce, for taking the time. And I want to say it is a fantastic book. You might mention that today is the official first day of publication.
Yeah, official launch day. It's been available for a while, but today's the day. So get them while they're hot, folks.
I can't recommend it enough. It is a fantastically written book that doesn't just get into material science or the geek stuff, but has a very human perspective. It contextualizes everything incredibly well. It introduces a number of voices, very well written. So thank you again, Bruce. Great to have some time with you today, and look forward to seeing what you'll continue to do going forward.
Thank you for having me. Thank you all for being here. It's been a pleasure.
Thank you to both of you. Thank you for spending your time with us today, audience. Take care.
Thank you, Lauren. Thanks, Andrea.
Thanks.
Thank you, Philip. Thanks, Lauren. Thanks, Andrea.
Thanks,
Be
Bruce.
well.
You too.